two circles can intersect either at 2 points, at 1 point, or actually have no points at all in common. Here's an example of two circles that have no points of intersection and they have different centers. When they have no points of intersection but have the same center, we call this concentric circles. One point of intersection are called tangent circles. There's two types of tangent circles. Those that are internally tangent, where one circle is inside of the other, and those that are externally tangent, where they are on the outside of the circle. 2 points of intersection are just what it says it is. There's nothing special about it. Copy this example down. In order to solve for this problem, we have AB that's tangent to the circle. We have a radius of 9 that is perpendicular to the tangent segment. This creates a Pythagorean theorem problem. So we're going to do leg squared plus leg squared equals hypotenuse squared. We're going to substitute in our information using our calculator and then take the square root. On this answer we won't have a plus and a minus because a negative answer would give us a negative length. Copy this example down. This one's a little bit trickier because the length of our hypotenuse is not an 8. That 8 is on the outside segment of the circle. So the 12 from P to R is a radius, so we'll need to add that all the way across with the 8 to get the hypotenuse. So this is a little bit tricky. That radius is going to give you trouble in some of your other problems if you don't watch out. Copy this example down. In order for us to decide if segment CB is tangent to the circle, we're going to check to see if it would make a right triangle. So what you do is test it out using Pythagorean theorem. 16 and 24 represent the legs. 32, we're going to test that to see if it's the hypotenuse. And what you do in your calculator is simplify the left side, then simplify the right side and see if the numbers are the same. And for this one, they are not, so therefore CB is not tangent to this circle. Copy this example down. This one we're missing the radius in the picture. You're going to have to expand out that r plus 16 squared like we did in an earlier unit. You've got r squared on both sides. Those are going to cancel, so the problem ends up not being so bad. It ends up being a linear equation. Copy this example down. A green on a golf course is in the shape of a circle. Your golf ball is 8 feet from the edge of the green and 32 feet from a point of tangency on the green. What's the radius? So here's another problem where that radius is missing. So one of the legs is the r squared, 32 is the other leg. R plus 8 would be the hypotenuse. You're going to have to square that r plus 8 squared. See if you can work this out and figure out the answer to these two questions. Copy this down. If two segments from the same exterior point are tangent to a circle, then they must be congruent to each other. I call these party hat problems. So one side of the party hat is equal to the other side of the party hat. Copy this example down. RS is congruent to ST because they both come from the same external point. So we set the two sides equal to each other and solve. Copy this example down. Same problem. We're going to set these two equal to each other and solve. When we take the square root, we get a positive and a negative answer. Will we get rid of the negative answer on this problem? The answer is no, because if I were to substitute a negative 3 squared back into the problem, it would give me a positive length. So this answer, I can keep the negative. Copy this example down. We're going to find the value of x. So again, these are two tangents that come from the same exterior point. So one side of the party hat is equal to the other side of the party hat. Now we've got a squared term and we've got an x to the first power and a constant. So this is a quadratic. We need to bring the 14 over, get it set equal to 0, and try to solve this. From our previous unit, remember we can try to complete the square, try to factor, quadratic formula. We can't take square roots on this one. I think you should try factoring. It does work very nicely. When you set each of these equal to 0 and solve, one of them gives you a negative answer. And if I were to substitute the negative answer back into AC, it would give me a negative length. So we can only accept the positive answer on this problem. Copy this example down. This is like a double party hat problem. You need to cover it up and only look at one party hat at a time. So look at the top party hat. If A to B is 3, then B to C would also be 3. Now look at the bottom party hat. E to D is 4, so C to D is 4. So all the way across would be 7. Copy down this problem. This problem's kind of like a trio party hat. In order to find the length of NP, you kind of start by covering up all these other party hats and just look at one at a time. Look at Q to R. If Q to R is 4, then S to R is 4. All right, all the way across, NR is 12. So 12 take away 4 leaves me with 8. If N to S is 8, then T to N is also 8. PQ is 10, so PT is also 10. So PN would be 18.